Good morning, everyone. I think we should get started. So I hope you're coming to the right room. So in this session, we're going to talk about optimizing OpenStack performance and TCO for large-scale private cloud. So first of all, let's give us a quick introduction. My name is Leon. I work for Intel as an enterprise solution architect in the data center group, primarily focusing on enterprise and government segment for data center digital transformation solution.
Morning. Morning, everyone. I'm Karen Chi from Cloud Data Center Inspur. I'm now leading an R&D team to support both private and public cloud based on OpenStack, Hadoop Stack, and other open source technology. Actually, I got my visa at the last minute, so I could make it to Denver to give this presentation with Dr. Xiang and Dr. Su.
Hi everyone. I'm Zhiyuan Su, and I also from the CDC group of Inspur, and I'm the architect of cloud product and the solutions. And our product is based on OpenStack too. Okay.
All right. The audio seems to have some echo on Dr. Chi. Can you try to set up? Thank you. So first of all, let us look at what is the China cloud landscape today. So why are we doing this large-scale private cloud solution? Because in China cloud, and why are we doing private cloud in China? Because in China, the public cloud is growing very fast, but the private cloud and hybrid cloud is also very popular and gaining a lot of momentum in China specifically, and depending on which industry you're talking about. So, and in fact, most of the industry that in China, they'll start looking at private cloud deployment. And according to some of the statistics that we have with our partners, like Inspur, as you see on the screen, there are more than 60% of the enterprise users are using open source cloud platforms. And one of the main reasons is because the safety and government mandate on the security and self-controllable, and to be able to modify the code in order to satisfy the security requirement being set off by the government. So in China, we see two paths here. One is the private cloud, one is the closed source private cloud, and the open source and the closed source. So on the open source, what we see here, OpenStack is a de facto, kind of like everyone's using OpenStack to build the open source private cloud. And next, I will let Dr. Su to talk about some of the enterprise private cloud requirement in China.
Thank you. So enterprise private cloud in China does have a very, I think, a broad market now. And I just take two industries as an example. The first one is one of our financial cloud customers, and its scale of the hosts will increase 6 times, and the VMs will increase 20 times in the next 3 years. That's a financial cloud of one of my customers. And the other one is the government cloud. The government cloud, I think the scale will exceed to 100,000 nodes in the future. So it is worth to mention that for both clouds, the open source technology and the OpenStack is always the first choice in these years. And since we come to the OpenStack, I think I will let Leo to talk about some insights about the OpenStack cloud market in China. Okay, Leo.
As Dr. Su mentioned, right, just now, actually the finance and government is just one of two examples that we talk about here. In fact, in China, there's many other industries such as manufacturing, retail, even automobile industry. They're all looking at using OpenStack to build private cloud solution. So some of the statistics that we understand from our partners is that the customer acceptance for OpenStack, as you see on the graph here, they're almost more than 40% in production today, and about 22% under the dev and development and testing environment, and 25% is about POC right now. But we see the trend is keep going up and keep growing the momentum to adopt OpenStack. And also, OpenStack is one of the fundamental core technology they use to build the whole full stack cloud solution. When customers want to deploy a cloud solution, they're actually looking beyond just the core infrastructure. So there are some other requirements such as the third-party security backup system, recovery, disaster recovery, the third-party software-defined networking solution, and load balancers and some of the PaaS platform as well. So the customer is looking at a complete whole stack, end-to-end stack solution to cover all the security, network, backup, all the features that you want to build around the OpenStack. But the key thing here is that using OpenStack as a core, as a central, to build around additional features around that. So that's one of the reasons that we work very closely with partners such as Inspur to build a whole ecosystem to satisfy the customer requirements. So that's the next thing I want to talk about, the overall open SDI cloud reference architecture. I think this diagram is not something new. To some of you, it might be very familiar. We look at the whole stack, right? So we're coming off from the bottom, the hardware platforms, because everything's run on hardware, whether you run on VM, containerization, or even providing bare metal services, right? Object storage and SDN services. Everything needs hardware. As you see, as you learned from the keynote session yesterday, right? So hardware is still the fundamental key things that you need to build your private cloud. You need to consider your performance, your total cost of ownership, and how to build that system, the full stack solution, using OpenStack as a core software solution, integrating with the hardware platforms, bringing in your compute, storage, and network, consolidating as a resource, and offer that resources to the customer on the top, that they run different framework and application at the top. That's what this diagram is talking about. So next thing, I'll let Dr. Su to talk about what customer cared about OpenStack.
Okay. Thank you, Leo. And actually, Leo provides us a comprehensive understanding of OpenStack cloud market in China, and I think I cannot agree more. So it's my pleasure to share about what our customers most care about the OpenStack cloud in China. And to conclude, we call it the triple H. At a large scale, you know the large scale. And the first and the very important, the most important H, I think, is the high availability. So as we can see, more and more production systems has adopted OpenStack as the cloud infrastructure, the technical, and also, the business, they cannot bear any interrupt. So the stability of the cloud infrastructure is very important. So that's the first H. And the second is the high efficiency. Today, the business of our customers is becoming more and more agile today, I think. So it also demands, it also needs the cloud infrastructure will become more faster and more agile. So we need a more high efficiency OpenStack cloud. And the third one is about the high performance, which I think includes some VM virtualization, optimization, and also like some real-time monitoring and warnings. So that's the triple H. And since we know about what our customers really care about, so what we should do now, and actually I would like to share some optimizations and practice in our software solutions. So here is a whole architecture of our software solution, and to meet our customers' needs, we continuously optimize the OpenStack around all three H. First, we keep HA always as the first-class citizen, and we introduce Misakari into our cloud solution, which is based on the Rocky version. And also, we carried out plenty of regressive and destructive tests at all the conditions to find out the weakness of OpenStack. And secondly, we, based on the CI/CD procedure and our understanding, our learnings from the community, we utilize Kola to build the images, and also we put all the images to the registry, which in the CI procedure, which is make it faster. And the caller and the caller symbol have been proved to be significantly efficient in our real practice. And more than that, other than that, we introduced some new features also. We introduced new features such as online VM expansion and intelligent image cache to accelerating the speed of instance booting. That's for the OpenStack solution. And also here, we actually believe that a good OpenStack cloud cannot be running without powerful and stable software-defined storage. So for this part, we, in our solution, the SDS, we call SDS, is designed with X-in-1 architecture, include the file, block, object, HDFS, and it can consolidate the application of multi-data sources with zero copy file, object, and HDF data in one system. So the InCloud SDS can support up to 100 billion files in one system. So that's almost all about our software solutions. Next, I will let Leo to talk about bring us some very exciting performance optimization from the hardware perspective. Okay.
Okay, we spent the first 10 minutes talk about requirements. We understand the needs of large scale in private cloud for China, private cloud, and we talk about performance. So in order to build a full stack architecture, software is important, or we cannot live without hardware. So when we add more and more, and we look at this diagram, right? When we add more and more SDI layer above or framework above, we're actually adding additional abstractions above every services. So one of my PhD researchers talk about adding, throughout the past 50 years of computer science, right? We keep adding abstractions above and make the user to easy to consume the services. But when we adding abstractions above, there are some of the features become difficult to expose to the upper layer. So that's what we try to do here together with our partners Inspur and Intel, right? So we try to increase the adoptions of we try to increase, make the platform features easier to accessible throughout that stack, the whole stack. And we want to increase that value of, at the upper layer application, we want to bring the best value of the platform features from the hardware into the application. But we have to pass through all the stack to make the users, make the application realize the benefit of it. So the next thing I want to tell you, this one is the Intel latest CPU. If you're interested to learn more about Intel latest second generation Xeon Scalable processor, go to the Intel booth, they'll tell you more about that. I'm not going to introduce the new CPU here. But what I'm going to tell you is more about the persistent memory. When we talk about performance, so the next few slides, I'll talk about more how we using the hardware latest technology to improve performance over TCO. How do you save TCO? And then later on, Dr. Qi will discuss about some of the large-scale environment that we talk about. So first of all, I mean, for performance, recently Intel just launched a new technology called the Intel Optane DC persistent memory. So this particular technology basically sits between the memory and the storage hierarchy. So it is faster than storage. The performance is near the memory performance. So by using this technology, we can help customers to save the overall private cloud TCO. So how do we save that? I'll talk about it a little bit in the later slides. So in the persistent memory, generally they have two operation modes. One is what we call the memory mode. The other one is what we call app direct mode. In the persistent memory that from Intel, there are three different types of capacity per DIMM. One is 128, 256, and 512 gig per DIMM. Okay. In the memory mode case, the persistent memory basically acts as a system memory. It's a volatile memory. Your operating system will just see that as a memory. And the DRAM within that system will function as a cache. So the overall, if you put the persistent memory in the full capacity, they basically can support up to 3 terabyte of persistent memory per socket, per CPU. So potentially one system set 6 terabyte. That's the thing that we can support. On app direct mode, basically, it's different from persistent memory. The memory will basically just function as a memory. So if the system reboot, right, you lost everything because it's memory. It's volatile memory. But for app direct mode, it's persistent. Persistent in a way that the application need to be persistent memory aware. What I mean is they need to work with the persistent memory through the SDK. There's an SDK provided so that you can do programming or changes at a code level, at the application level, to write directly into the persistent memory. When you write directly into the persistent memory, you get the memory-like performance, but you also get a storage-like persistent. Even the system reboot, you still have the storage. You still have that data in that persistent memory. So you get the best benefit of the memory-like performance and also the persistent. So TCO. Sorry, I got a flu yesterday. So TCO, memory mode. In a DRAM system, we did some comparison between a full DRAM system and a mix with DRAM and persistent memory system. So in the DRAM system, we understand that the price will keep dropping today, but based on the figure, based on the number that I have when we run this experiment, in a DRAM system, the cost of providing a DRAM system is slightly the same as the cost of using the mixed DRAM and persistent memory system, depending how you configure it. So if you compare these two systems, the price is actually, maybe the persistent memory might be slightly expensive, just by a little bit percentage. But but that allows you to put more VM on that host, because potentially you can support up to 3 terabytes per CPU. So if you put that into a different, there are different configurations that you can work in a memory mode. With that, right, if you have more memory, in a system, you can put more VM or larger VM on that system. That help you to do more and save more. So of course, the persistent memory in this capacity is basically positioned as a large memory. And the good things about this configuration is that there's no software or application changes is required. If you have a private cloud today, if you plug in the persistent memory, it will just function as is. There's no code changes is required. Okay, but of course you need to configure the persistent memory to behave like a memory mode. The next one is the app direct mode. App direct mode basically is like back addressable like a memory. It's persistent like storage, as I mentioned just now. But one key thing here is in order to utilize these features, your applications such as Redis or Spark, they need to be they need to be make changes to that code in order to write directly into the persistent memory module. The good news is we already upstream the persistent, the PMM features into many of the applications, including Spark and Redis. So today, if you want to run Spark with persistent memory, there's already upstream patches that are available that you can use and take advantage of the persistent memory app direct mode. So in app direct mode, there's also one function or features that you can do in app direct is to use these as a block devices. In this mode, it is an app direct mode, but it appears as a block devices like SSD or HDD. So if you do an LS block, you will see that as a block devices. And in this mode, no changes to the software as well. But you won't get the same performance as what you have in the app direct mode that I mentioned previously, because it goes past through all the OS systems. So this is one of the work that we have been working with. Our team has been working with the upstream in the Nova community. We try to bring in this persistent memory for the app direct mode to be able to utilize by the VM layer. I mean, for memory mode, no changes required. But for app direct mode, yes. For app direct mode, we need to be able to expose the persistent memory region and every namespace into the VM so that the application running the VM can consume the persistent memory directly. So this work is still ongoing. There's some blueprint and code patches on the link that you can see on the screen. So that's about the performance we talk about using persistent memory. So next thing, I'll pass on to Dr. Qi to talk about performance at scale.
Thanks, Leo. It's my turn to verify the high performance, high stability, and high efficiency at large scale. We designed a comprehensive test, including control plane concurrency, data plane performance, as well as operation efficiency and high availability. With the help of Intel team, we built a 200-node cluster. As illustrated in this page, we can see the topology of the cluster. There were 5 controller nodes, 3 isolated authentication nodes, database node, RabbitMQ node, respectively. In the data plane, there were 140 edge computer nodes, each was configured with 2 Xeon CPUs and 256 GB RAM. The cluster also had 30 storage nodes. Each had 8 SSD disks. From the point of view of network, we use the 1 gigabit network as the measurement network and the 10 gigabit network as, to accommodate both time network and storage network. To be specific, as for efficiency at large scale, based on our highly optimized tools based on PHRE, boat, and class symbol technologies, we could deliver hundreds of nodes in 1 or 2 working days, including deployment, reconfiguration, upgrade, and even scale out if necessary. In our 200-node case, we took about 55 minutes to install operating system, 20 minutes to distribute the container images across the cluster, 8 and 90 minutes to set up the SDS and ICOS cluster, respectively. Furthermore, during our test, we continuously adjusted the configuration for better performance. It took about 35 minutes on average. As for control plane performance, we conducted 20 cases under 2,000 concurrent requests with Relay, including the actions and operations of instance, volume, network, etc. And our system can successfully pass all the cases. In the data plane I/O test, we set up to hit the 30 nodes SDS by up to 32 clients. Each host 10 FIO instances. As we can see from the plot, the overall performance is pretty good to meet the SLA. Specifically for the random read case, the performance can keep nearly linear increase until 320 VMs, which is throttled by OSD CPU. For random write case, the performance started to decrease at 8 FI client, and the system resource had not been fully used. So there is actually no hardware limitation, and the SDS software itself still has much room to improve. For 1 megabyte sequential write and read case, the scalability is pretty much the same as the random read case, but is throttled by SSD and network hardware, respectively. In our latest ICOS version, we also enable Octavia as our load balancer service. And to establishing the performance baseline, we used distributed VGET as a workload runner, and fine-tuned NGX instances as per members. And to get better performance, we try to optimize the performance of Inspur. Yeah. And the main step we did is to upgrade the HA proxy from the version 1.7 to 1.8 to take advantage of the multiprocess and use the CPU pin flavor to build every instance. As a result, the optimal concurrent rate is about 100,000, which was fronted by the VXLAN type network model between the ARB service and the backend. Okay, of course, we encountered several bottlenecks during our test, such as DB deadlock and IP allocation collision problem. Here is an example how we deal with, how we solve how we debug the IP collision problem and collaborate with the community. The IP collision problem was first encountered when we perform the 800 concurrence test. We found a similar, fortunately, we found a similar bug report on LagPad, and we backported the code into our environment. However, unfortunately, though the IP collision problem disappeared, the success rate cannot reach 100%. So we trace the debug log again, and the ultimate reason is that the placement API worker is not sufficient. So we increase the worker number, so the problem solved. By the way, the bug fix algorithm is mainly about increase the retrying times and the interview to avoid IP collision. Our network team is working on solve this problem use another way. We are trying to use the distributed lock mechanism to solve the problem, which is more effective in the high concurrence scenario. And maybe we can see the BP later. Okay, of course, during our experiment, a bunch of parameters have been taken into consideration from operating system layer to all OpenStack components, such as agents, schedulers, API servers. For example, to take full advantage of the multi-core architecture, we adjusted the worker-like parameter for all the controller nodes. For more performance results and tuning results, you are welcome to contact us or visit the Intel booth. And by the way, we are performing a larger scale test, which is bigger and larger than this cluster. Maybe we can share this detail in Shanghai. Okay, at last, I'm glad to share a success story based on the OpenStack, the above mentioned open source SDI solution. With the ICOS and SDS software, we built a production cluster for one of the top 6 banks in China to support their mission critical applications in production. For now, the cluster had been scaled out to almost 1,000 and can actually guarantee 5-9 high availability. We also built active data centers in one city and disaster backup center, which in another city, which is about 1,000 kilometers from the other two, and cascaded monitoring architecture was also implemented to provide a unified monitoring view. Okay, that's all. Let's give it back to Leo.
Thank you. So I'm going to wrap up these sessions. So we talk about China, private cloud, the large-scale requirement, the performance and TCO when, the importance of the performance and TCO when you're building a large-scale private cloud in a 200 nodes, 500 nodes, or even more than 1,000 nodes environment. You need more VMs per host. We talk about how to use latest hardware technologies to help you to save the TCO and performance in combination with the software architectures, using OpenStack as a core underlying SDI infrastructures, combining that with hardware platforms, exposing all the hardware features through the OpenStack SDI, and providing the benefit to the users. We also talk about the test scenario that we have done in the past. We share some of the configuration parameters. I mean, the default in OpenStack documentation, the upstream documentation, there are quite a few parameters that you need to be aware of, because some of the default numbers, the default value, is not sufficient. You need to tune that values, especially when you're deploying in a more than 200 nodes environment. Okay, so if you're interested to find out more, come to us. So I'll be at an Intel booth for the most afternoon today and tomorrow, and you can contact me, Dr. Su, Dr. Qi. I think we have an email at the beginning. So welcome to reach out to us if you have any questions. I think we have 5 minutes for Q&A. Is that right? Yes. Sorry. So that's my email and Dr. Qi and Dr. Su. Feel free to reach out to us if you have any questions. Open for Q&A. You got 5 minutes counting down. Go ahead. There's a mic in the middle. Yeah.
So in the 1,000-node cluster,
1,000-node clusters?
SDS nodes, how many were the safe nodes?
How many is the safe node SDS? In the 1,000-node cluster, how many is the storage? 存储有多少个节点
？30 storage nodes actually.
你在那个 1,000 nodes 那1000节点的1000节点那个 case 里面。
Actually, there is several kind of storage, including SDS. There are other centralized storage such as Inspur, as other vendors.
有多少个节点？
It's about for SDS is about 8 nodes, I think.
8.
Yeah, 8.
Thank you.
They have non-share storage, not more than SDS. They have different kind of storages.
Yeah.
They have centralized non-share storage and based on the FCSAN, IPSAN, and also the distributed storage SDS. So different storage nodes in that environment. Okay.
Any other questions? Can you speak to the mic? Oh, okay.
Persistent RAM, I guess.
Persistent memory. Persistent memory, yeah.
Does that have the lifespan of SSDs, or does it have a lifespan of RAM?
There's a number, so that I don't have that on my mind here. I can share the information with you later on. So there's a data talk about the lifespan. Yes.
More like SSD.
SSD.
Also, for the persistent memory, what did you do about managing live migrations?
Sorry, come again?
For the persistent RAM, what did you do about managing live migrations?
You mean in the app direct mode or in the memory mode? In the app direct mode, I think the team is still trying to figure out, but it's not right now. I don't think it's supported yet for in the app direct mode. But I need to check with that because the upstream team I'm no longer participating in the upstream activity. So we get our Intel engineer to get back to you on that. Yeah, you can reach out to me. But as far as I know, I don't think they cover the live migration for the app direct mode yet. But that's definitely in the scope. Yeah. Any other question? No? Okay. So if you have any further questions, feel free to stop by our Intel booth. I'll be there most of the afternoon and tomorrow as well. With that, thank you very much.
Thank you.
Thank you.